Okay, so we are jumping into chapter 3 in this video. And in chapter 3, we're going to talk about a really important concept for analyzing two quantitative variables, which is the scatter plots. And in this unit, we're going to do a lot of stuff with scatter plots, lines of best fit, things you've seen before in algebra and algebra 2. But naturally, in AP Stats, we're going to take those concepts and go a lot more in depth than what you guys are already familiar with. This first lesson, though, is just kind of getting into the basics of what we use a scatter plot for, and how you describe or analyze what you see in a scatterplots. So, why do we study the relationship between two variables? In our last couple chapters, we've been looking at essentially one variable at a time. Our last unit on the normal distribution, we would have one variable going this way, whether it be test scores, heights, whatever. We just look at one variable. But we may want to look at the connection between two different variables at the same time. And there's a couple of reasons why you may want to do that. So one thing you can do is to see or to explore if there are connections. So discover connections between different variables. So one big thing, not the only use of this, but cause and effect is huge. Like knowing that one variable causes another. If I do this, then this is going to happen. You would want to analyze how those two variables are related. But we've talked about how even if there's not a direct causal link between two variables, they still may have some sort of a connection right here, where if you know this one, you have more information about this one. That idea of an association that we talked about. So you may want to know how these two variables are going to relate to each other, and that can help explain stuff that's going on. You can also use it to make predictions about the future. So if I know that one variable is going to have some sort of an impact or tell me something about the other variable, I can make predictions about what's going to happen later on, which is pretty valuable. So we want to be able to explain what's already going on and discover if there are connections going on between variables, and we want to be able to use those connections to make predictions about the future. We've already talked about this next point before, so this is a complete review. When you define your variables here, the explanatory variable is going to be your x, and the response variable is going to be the y. The response variable measures an outcome of some sort. So it's whatever you're trying to measure, whether it be test score or, I don't know, gas mileage, anything really. So your response variable is going to be the outcome you're trying to measure. And then your explanatory variable, which you can have one or you can even have multiple explanatory variables, are seeking to explain why you're seeing the response that you are. So they're seeking to figure out if they contribute or not to the response variable. But we've talked about those before. When you want to analyze two quantitative variables, recall quantitative means that they're both numbers. The only way to do that is with the scatterplots. Okay? If you want to look at two variables that are numbers and compare them, you need to make a scatterplot. And then once you have your scatterplot, you can do all sorts of fancy math with that. In chapter 1, a little while back, we talked about two categorical variables, and that's when we made those percentage-based conditional distributions, and we looked at like the segmented bar graphs, the mosaic plots, and stuff like that. So that was two categorical variables. But if you have two variables that are both numbers, you have to bring in scatterplots. So with that being said, if scatterplots are going to be so important, let's learn a few rules and learn how you actually describe a scatterplot. So this should be pretty basic. You guys have all taken algebra 2. How do you know which variable to put on each axis? X is going to be your explanatory, and Y is going to be your response. So that is not a big deal at all. You guys should already kind of know that. Where do you start each axis? You can start it wherever you want. So anywhere you want to start each axis is totally fine. Back in algebra 2, when I taught you guys scatterplots, we would put like the little squiggle bracket, like break in the graph thing and start at whatever number we wanted to. You don't even have to do that in an AP stat style scatterplot. If I want to make this 30 and make this 72 or something like that, I can totally do that. But you still need to make sure your tick marks go by the same amount. So if I went by like 2s here, you're not really supposed to do breaks in the middle of the graph. So just basically start where you want, but don't throw a break in the middle of the graph. You guys already know how to make scatter plots pretty well, so this should not be too big of a deal overall in this section. So, bottom part right here, what is the easiest way to lose points when making a scatter plot? Forgetting labels. What do I mean by labels? I mean two things. One, make sure you actually number your tick marks like I'm doing right here, so it's very easy to see what's going on, but also writing down what your variables stand for. So I don't even know, this could be like miles per gallon or something. I don't know. Like writing down the context for what your variables are going to be. You got to make sure you include context and label your picture really well. So we've got a sweet comic giving a shout out to XKCD. Great math science-based comics if you guys ever want to take a look. But looking at these two right there, in class I like to like act this out and show you guys what's going on. So I'll do it in the video as well. There are these two people, and oh, she thinks that we should break up, but he's like, oh no, we should give it another shot. But she made a graph to show him why they shouldn't break up, or why they should break up, sorry. And it's our relationship, and you can see it kind of goes down here along the graph. He looks at it, and he's like, oh gosh, maybe you're right, we should break up. And she's like, man, the data convinced you. And he's like, no, you didn't label your axis. So basically, long story short, you guys never know when it's going to be important that you actually label your graphs. All right. So let's go ahead and look at an example right here. And you guys know how to make scatter plots, so this really shouldn't be too big of a thing for you all. I'm going to pause the video after I talk about this here and just put the example, like put the scatter plot on, and you guys can do likewise. When you make one of these things, you're first going to want to decide which variable is which. And in Algebra 2, I would talk about which variable affects the other. I was very like not cautious with my language there. In AP Stats, I'm not going to do that because we don't know that this is like a cause and effect type of deal. But what I'm going to think of is asking myself, which variable makes more sense that it could affect the other one? Or which one is more likely to be the explanatory in this problem? Is it more likely that sprint time, how fast I am, affects how long I can jump, how far I can jump, or that how far I can jump affects how fast I am? And it makes more sense that if you can run faster, you're going to jump farther. So this is going to be my x. Oops. I'm going to have sprint time on my x, and I'm going to have long jump distance on my y. Again, when you do this, you can choose whatever starting point you want on your variables. I'm going to go ahead right now, though, and put my contexts. So I have long jump distance in inches, and then I'm going to have sprint time in seconds. And I think I'm going to choose with this problem. Looking at my numbers, my lowest is a 5.05. So I'm just going to start at 5. That's nice and easy to work with here. And I'll have to decide. I don't want to get too like crazy with my tick marks and make like 5.1, 5.2, because that's going to take forever. But as long as I'm consistent, I can do what I want here. My biggest is a 7.2. So I'm going to be a little bit lazy on this one and go like 5 to 5.5 to 6. In Algebra 2, we would have talked about using the full picture here when you make these things. So I'm spacing my tick marks evenly, hopefully, but I'm trying to spread them out well enough that I can use most of my axis right here. And then I have my long jump distance on the y. My lowest number there is a 65. And I got to get all the way up to 184, it looks like. So I'm going to go by probably tens on this. So I'll go ahead and pause the video and come back with a completed scatter plot, and you guys can pause the video and graph this yourself. Okay, so I'm back now with a scatter plot right here. A little bit messy, just hard to draw on the, like, if we really wanted to make an awesome scatter plot, we would use grid paper and it would look a little nicer than this. But just key things to highlight right here. I realized after I started that going by 10s was a lot of tick marks to squeeze in here, so I could have just been lazier and gone by 20s. I might also, if I had redone this, gone by like 180, 170, 160, like clean 10s rather than 5s, just because it'd be easier. But really, honestly, you know how to make a scatter plot. I'm not going to make you make a bunch of scatter plots. Just use common sense that's gotten you this far in math, and you should be just fine. So when you are in AP Stats, the problem is never going to be, oh, make a scatter plot, done. They won't, like, the purpose of the problem isn't just to make a graph. It's to use that graph to analyze what's going on in this situation. And if we look at this picture right here, The first thing we should ask ourselves is, does there seem to be any sort of a pattern? And the answer to this is yes. There's a pattern where the points are going downwards along right here, which, as you guys might remember from algebra, is a negative correlation or a negative pattern. Basically, when one variable goes up, so like when my sprint time goes up, or if I go right, my jump distance goes down. So if your sprint time goes up, that means you're running slower because it took you more time to get the same amount of distance. So basically, if you run slower, it makes sense that you wouldn't jump as far because you're not getting as much speed when you actually take off. Whereas if you run faster, it makes sense that you would jump longer. So that seems pretty reasonable to me to say that, yeah, there is some sort of a pattern between those two variables. Faster time means longer jump. Slower time means shorter jump, like that. If you think about what else we might want to know from this picture right here, we can say, okay, yeah, there seems to be a pattern. When one goes up, the other goes down. But what about, like, is it a good pattern? Is it a strong pattern? Is there anything else going on? So something else we might want to know about in this picture is how closely do the points follow the pattern? And we did this a little bit in algebra when we talk about the strength or how closely my points follow this overall pattern right here. These points are reasonably packed together right here. It's not like they were spread all like this as well, where the pattern gets blurrier and harder to see. So we want to know if there's basically going to be something positive where it's going up or negative, like we talked about. We want to know how closely those points follow the pattern. We also want to know if that pattern is just basically a line, or is there some sort of like a loop or curve to it? Like if my data is going like this, I can talk about, oh, it goes up and it comes back down. That would be a useful thing to know. Or if there's something else that's not just an obvious line. And the last major thing I might care about in a scatter plot problem is if I have any points that are just way different than all the others. So if I have a kid who's way over here, really not very fast, but they just jump a super long way, that might be noteworthy as well. So that would be considered an outlier, or as I'm going to define it in a second, an unusual points. So there's a lot of things you can talk about when you have a scatter plot, and we're going to define the 4 big things that you need to do to fully analyze a scatter plot on the next slide. So when I look at my next slide right here, we had for regular quantitative graphs like histograms, SOCs, shape, outlier, center, spread. We have 4 characteristics you're expected to talk about with a scatter plot, and I don't have as great of a acronym or whatever for that. My kids last year decided that they liked FUDS, F-U-D-S, to remember these. Duffs, whatever you want to call it, with those 4 letters right there. But these are the 4 things that you need to be able to do in a scatter plot problem. When we talk about the direction of a scatter plot, we're talking about whether there appears to be a positive or a negative pattern to the data. So your direction is either going to be a positive or negative, or it could go positive to positive or something like that. So it's basically what direction your points are headed in general. Form is going to talk about whether the basic pattern is linear, or it could be curved, or it could be exponential. If you want to get like fancier and use like, I don't know, algebra 2 vocab, you could have a quadratic form and stuff like that. Basically in AP Stats, though, we don't worry too much about fancy things like exponentials and quadratics. We'll primarily focus on linear and curved patterns. So the other stuff, is it exponential form, etc., won't really come into play. You can just call that curved. Or another way of saying curved is going to be non-linear. So linear / non-linear is going to be probably the biggest extent of what we do there. We also, when we talk about form, we'll talk about something called clusters of points. So we'll also talk about clusters, which I'll address on the next slide when we see our example. When we talk about strength in a scatter plot, we are talking about how closely the points follow the pattern. So how closely points follow the overall pattern. So when I talk about that, you're talking about having a strong, a moderate, a weak, a no correlation, or you could say like moderately strong or relatively weak or stuff like that. So there's basically these kind of words here for how closely your points follow the pattern. And then finally, the fourth thing we'll talk about is what is considered unusual points. Unusual points can mean outliers, but it doesn't have to be. We're going to do a lesson later on in this chapter where we learn like specific terminology for like outliers, other things called like high leverage points. So unusual points are just weird points, and we're staying away from the word outlier for now. So outliers / other noteworthy points. And like I said, we'll do a lesson on outliers and stuff like that at the end of this chapter. So these are the four things, FUDs, or however you want to remember it, that you have to address when I ask you to describe a scatterplots. So most of the time in AP Stats, I'm not going to make you make a scatterplot. A problem isn't going to have you make one from scratch because it's really tedious and it takes a while, and it's just easier if we're all analyzing the same thing. In real life, if you were analyzing data, the computer would make the scatterplot for you. So you can expect that a problem will generally give you a scatterplot that's labeled and everything, and your job more often than not will be to describe what's going on. So it says to describe the relationship between sodium and fat in these different salads at McDonald's here. So we've got our sodium in milligrams along the X, and we've got our fat along the Y. So I'm going to talk you through this, and we'll talk about all these different features. Then I'll pause and just have a nice written up solution that you guys can look at here. So when we talk about one of these problems here, FUDS are going to be the four things that we'll talk about here. So thinking about what those mean, the first thing I'm going to address, I like doing direction first. It looks like overall there does appear to be a positive pattern to this data set. Now, if you look, this is not a data point right here. This is just 0, 0. So we can ignore that guy. Our points, instead of just being one kind of continuous spectrum right here, we kind of have three separate, what are called clusters of points. I'll address those when I get to form in a minute. But when we talk about the direction, positive or negative, for our setup right here, we can talk about the overall pattern, which overall, it does seem to go low to high, and it does seem to be a positive direction there. But you can also talk about within each cluster. Inside each bubble, it's also going low to high, even though there's only 3 data points apiece. It is possible to have a scatterplot scenario where you've got like separate clusters like this. So your overall trend, if you look at just all the dots, does still appear to be positive right here. Still a relatively positive pattern, but within each cluster, it's going negative. So you can have a situation where there's a difference there, and you just talk about both of those if that's the case. But in my problem right here, both within the clusters and overall, it appears to be positive. So in my little list right here, I'm going to write up a nice response, but I'm going to talk about direction being positive for both inside the clusters and overall. Next up, I'm going to talk about form here. The order isn't that important, which way you do it. With form, again, you look overall and you look within the little clusters and see what's going on. Overall, if you look at all these data points, it seems to be somewhat curved. If I look at my data set, it seems to go something like this overall. But if you look inside of each separate cluster, there it seems to be more or less linear. Mostly straight, mostly straight, mostly straights. It's worth noting when we talk about things being linear, they can be really spread out as long as there's not a better pattern. Like let's say this part of the data looked like this, that I would still consider linear, even though they're not very close to a line right there, because it's not like there's something better than a line. They still kind of go like this overall. So anyway, long story short, the overall pattern, I would say, is nonlinear. But if you look within each cluster, that is going to be linear. So overall is non-linear, but clusters are linear. I'm also going to talk when I write my response out about just identifying that there are 3 separate clusters of points. Okay, so I'm going to talk about how there are 3 different little pockets of points right there. Next up is my strength. Again, I can talk about overall strength, and I can talk about strength within the bubbles, although there are only 3 points apiece. But I would argue that the overall pattern here is fairly strong. So like if I were to draw a line like this, most of my points are pretty close to that. So it's an overall pretty strong And then within the cluster, it's also strong, but there's only 3 dots, so I'm not going to bother talking about that. The last thing I need to talk about are my unusual points. And this graph right here doesn't appear to have anything that like blows my mind with just how far away it is. This point is a little bit separated from these two right here, but it's not like there's a dot over there or something. So when I get to unusual points, I'm not going to talk about anything too crazy. So I'm going to write up a nice response with all these things and comment on a few things after I do that. So you guys will see me in a second, and then I will talk about it. All right, so I'm back with the solution right here. Not that this is like word for word what you would need to write to get full credit, but it hits on a lot of the key points. It hits on everything you would need to have right there. And I'm just going to comment on a few things with regards to this answer here, but copy this down so you have a model solution. And when you're doing your own problems on like homework and stuff like that, I recommend using this as one that you look at just so you can see what it takes to for sure get full credits on a problem on the AP test or on one of my tests. So when I do these problems here, I don't usually like to separate them to each one like I sometimes do with SOX problems because I find that I repeat myself a lot when I do. So I like to start with one sentence that just hits all the key points. So I talked about strength right there. I talked about the overall form right here. You could say nonlinear or you could say curved, and either would be acceptable. Talked about direction. And then I added in a little bit of context here. This next sentence is really good and frequently is like the difference maker between partial credit and full credit on AP test rubrics. As sodium increases, so as X increases, Y also tends to increase. Or if it was a negative association like the last one, as sprint time increases, your long jump distance tends to decrease. That's just a really good sentence to have in there that gets you really good context and sort of shows that you know what's going on with this problem. This data set happened to have clusters. So if this was last scatter plot, I wouldn't really have to do this part right here. But since there were clusters, what I did is I addressed about roughly where each one was located. And then I also talked about the pattern that we addressed above within each little cluster right here. Inside the clusters, there was a positive linear association. So I talk about that as well. And then I tossed in at the end, I probably should have said there don't appear to be any, but there are no unusual points that I can see in this scatter plots. Incidentally, and this is just something I didn't write in there, but just for your own information here, when you see clusters, part of the reason we care about like identifying them is there may be some other variable that we haven't considered that's actually responsible for why the data appears in different clusters that we didn't already look at. And it turns out that the variable of interest that the clusters kind of come from is whether or not there's chicken in the salad and what type of chicken it is. I'm pretty sure these were no chicken salads right here. So very low sodium, very low fat. These ones were grilled chicken. So grilled is lower in fat. And then these ones were going to be, I think, fried chicken. So lots of sodium and lots of fat. So the type of chicken in the salad made a difference in where those points were located. So we identify clusters so we can look for other variables of interest. And that is just a basic introduction to how you should describe a scatter plot.